All right, folks, let's get started. So we'll start diving into the meat and potatoes of this class today. The fun time of videos and entertainment are over. I'll try to be as entertaining as I can. As a geek, as an geek can be. So in this course, we talk about signals and systems. So let's put together a picture about what we mean. And the primary view we take of signals and systems is one of input and output. So we have a system. We usually give it a name. Let's call it F, to which we apply a signal, and this signal may be a scalar valued signal or a vector valued signal. In this class, we usually talk about a scalar valued signal. So x is some function, and y is some function. This function x is called the input to the system, or input signal. And the response of the system to this particular input signal, we denote by y, and we call it the output signal. Okay? Now, I don't want you to be wedded to these symbols, x and y. One of the tricks that our former department chairman Edward Lee played on his students on a midterm once was to call the input y and the output x, and that threw off half the class. So it's important that you understand the concepts and not be wedded to symbols. We, of course, try to make the symbols as intuitive and clean as possible for you. But what's important is that you understand the underlying concepts. Now, this signal x comes from some kind of a set that we call x, and I sometimes write it over here. So this set x has a whole, is a set, each of whose elements is an entire signal. So I can have an x1, x2, xn. Now I'm cheating a bit here. Remember I said your education is a process of diminishing lies. I've drawn this as if I can count the number of elements in my space capital X. That's not necessarily the case. In fact, a lot of times it is not the case. But it serves to, it illustrates the point that each of these input signals that I apply to the system comes from a set that I will call capital X. And the system takes each of these signals, or each of these functions. So each point here, each marble in this bag, represents an entire function of, say, time. The system takes each of these and maps it to an element in an output signal space y that, for notational purposes, I will name y1 as the output corresponding to the input x1. So let's write some definitions here. X capital is the space of input signals, or input signal space. Or input signal set. And y is the output signal space. And so your system now becomes a function that maps cap x to cap y. So this is a function remember from your math courses that a function has a domain. And a range or a codomain. And I know a lot of you math freaks want to distinguish between codomain and range. We don't care about those things in this class. You can call it whatever you want, or range. What's important is that you understand, and if you're rusty with it, review the properties of a function. A function is a mapping that takes an element in its domain and maps it to an element in its range or codomain. It's got a name. We've named it f in this case, domain, range. And then beneath that, there should be a rule saying how do you map each of these to each of these, or to some subset of y. What's important is that a function, by definition, must tell you what it's going to do to every element in its domain. In other words, no element here ought to be left an orphan. Your rule must make it clear what it's going to do to each and every one of the elements in your domain. So every element in X must map to an element in Y. And then in parentheses I'll say, but not every element in cap Y is mapped to, is necessarily mapped to. Okay? So far it's very high level. You've got this black box that we call a system. So far you've learned that the system is a function. It takes some signal applied to it as an input, and in response to that applied input, it produces some signal in the output. And I represent an entire signal in the input and the output with points in the corresponding sets X and Y. So here's capital Y. Now, what are some of the types of elements in cap X that I'm talking about? I'm not going to go into the particular rule that says, how do you map X1 to Y1? We're not there yet. X, we said, is a signal, and we use the terms signal and function interchangeably in this class. Any signal is a function, as far as we're concerned. Signal is a function. So if signals are functions, then they too must have a domain and a range. If I'm talking about a voice signal, what would be the domain? Time. So time is a continuous variable. And so we can say, okay, the domain is the set of real numbers. And the range, at least in the examples you saw last time, were what? Amplitude, and that's coming from what kind of a set? Reals. Okay? Signals could also be complex valued. All right, so we can draw such signals. So here's the t that we use to represent the argument or the variable that comes from the domain of X is a continuous random variable. It's selected from the real axis, from the real line. and the function takes on some values. So this kind of a plot would be a plot of the instantaneous values of the signal x at various times. We usually in this class use time as our argument for signals, at least in continuous time, but it need not be so. I can be talking about x if it's representing the thickness of some pipe, will be the differences in the thickness, or will be the spatially instantaneous values of the thickness of the pipe as you go from, say, 0 to 10 meters. This is an example of an analog signal. An analog signal is a signal whose, so if I generically represent the signal x as a function going from domain, well, let's make the notation easier too. No, let's keep it AB. It's simple enough. An analog signal is a signal whose domain is uncountable and whose range is uncountable. What do I mean by uncountable? What does that mean? I mean, you don't even have to have read Appendix A to make a comment on this. What does uncountable mean? It's got some kind of a, well, what can you say about the size of the set? If I say a particular set is not countable. It's got an infinite number of elements, okay? And not all infinities are equal. Some are more infinite than others, okay? The set of real numbers has an infinity of points. The set of integers has an infinity of points. What's the distinction? One is countable. You can say 1, 2, 3, 4, and so on. Whereas with the real axis, with the set of real numbers, you can't do that. So analog signals are signals whose domain is uncountable and whose range is uncountable. Digital signals, on the other hand, have both countable domains and, countable domains, and the range is not just countable, it's more than just countable. It is finite. What is a finite set? How many elements does it have? A finite number of elements. Right? 1 through 5. A binary signal has how many elements in its range? 2. 0 and 1, or 1 and minus 1. Right? So an example of this would be a signal that takes values among the integers and maps it to, this is an example, 0 and 1. Now the way we plot these is something that you've probably not seen before. So let's do that. Actually, I can do it here. We typically use indices such as k, l, m, n for integers. And variables such as t in that board for continuous variables. So the way we plot signals that take on a countable domain is by what we call a lollipop plot or a stem plot. This is a stem plot. This is the more respectable name for it. But in this class, I won't dock you if you call it a lollipop plot. So if I'm plotting a binary signal like this, it'll be something like this. So this would be 0, 1, 2, 3, 4, minus 1, minus 2. And I put the value next to the lollipop. And if it's 0, it's clear. Okay? So this is an example of a digital signal that's whose domain is a countable set, namely the integers, and whose range is a finite set. So let's say this, by finite we mean a finite number of elements. A finite set by definition is also countable. Not every countable set is finite, but every finite set is countable. Okay? Now, we don't get hung up on digital and analog in this class. The classification that we use most frequently is what we call continuous time and discrete time. And again, keep in mind that even though we use time in our nomenclature, all the principles we use apply to other units, such as space. But time is a convenient variable to use. So a continuous time signal, x, is a signal that whose, so x, let's name it here, x from A to B, x from A to B, A is uncountable. We remain silent on B, the range. So continuous time signals are signals whose domain is uncountable. Examples are A equals the set of real numbers, just like this function that I drew earlier. Where is that function I drew? Oh, it's up there. Yeah. So every analog signal is a continuous time signal. A discrete time signal is a signal whose domain is countable. Again, we remain silent on the range. So every discrete time signal will have a lollipop plot, if it's real valued. But we're not restricted to a finite set of values. The values that these lollipops can take, which we represent by their respective heights, can be taken from the set of real numbers, can be taken from the set of complex numbers, or they can be taken from a finite set. Okay? All of those we bunch together. So this one could be 2 at minus 1, 0, 1, 2. And this could be root 2. This could be minus 1 over e. There's no restriction. Okay? Yeah, you can have imaginary values, but it's kind of awkward to write an imaginary number here and represent it with a height. So the lollipop heights we usually use this kind of a plot for real valued signals. Things also get complicated when you have the signal mapping to a set that's two-dimensional. Or well, actually, two-dimensional is okay. Three-dimensional, gets hairy. Four-dimensional, forget about drawing it. Okay. So I've been talking about one-dimensional signals, namely the domain is a one-dimensional space, like the real line, and the range is real in the examples that I've drawn. But, for example, when you're talking about an image, what are the dimensions of your domain? 2. You've got a horizontal axis and you've got a vertical axis. Then, in that two-dimensional grid, you've got to say what the value of each pixel is. And that can be real valued, or most often with color images, you need to have 3 values. So the value corresponding to each pixel will actually be a vector of 3 values. So things can get hairy, but to keep the math simple, we'll stick with one-dimensional for the most part. You will have labs in which you fiddle around with images. But by and large, in lecture and in discussion sections, we'll talk about one-dimensional signals. And you're way tardy with your bonsai break. All right. Okay, folks. Let's resume. I got a few questions about this finiteness and countability. This remark that I put in parentheses is very important. It's not the magnitude of the numbers in the set that I'm talking about. It's the number of elements in the set that has to be finite. Okay? So when I'm talking about a finite set, I mean when you look into the bag, there's a finite number of marbles in there. Okay, 1, 2, 3, 4, 5. Or in this case, 1, 2. There are only 2 elements. Okay? That's what's important. And inherently, a finite set must be countable. Yeah? Yep. I certainly can. Yep. Yeah. So in this discussion, we're talking about the number of marbles in the bag, the number of elements in the set. Now, part of the reason we don't harp on the definition of an analog, well, analog signal has no controversy around it. But the notion of a digital signal is something that there is no universal agreement on. So the way I defined the digital signal, where was it? Well, here. Sorry, I need to take a step back. The way I define the digital signal is what I prefer, because a digital signal you can store in a computer. That's going to be the criterion I'm going to use. You can store these elements in a computer because it requires finite precision. If the values can take on an uncountable, a non-finite but countable set of values, you can't store it in the computer with finite precision, unless you quantize, unless you do some kind of approximation. And similarly, if this is the set of real values, then you certainly can't store it in a computer without doing additional processing. Yeah?
I'm kind of confused about your marble analogy. So if 0 and 1 are the number of marbles, then what the hell is n?
N comes from the domain.
N comes from the domain, but then you just said the domain is just 0 and 1.
No, that's the range.
Okay,
if I said domain, I misspoke. This is the range. This is the domain, this is the range. The range has 2 elements in it.
All right, so domain is like the number of marbles, and your value...
No, the range contains the number of marbles is the set of values that each of these lollipops can take. Okay? So I'm looking at that. I'm looking at that as a set. Well, actually, each set that's countable, you can think of a bag having marbles in it, right? Except when I'm talking about a finite set, I'm looking at a bag that has a finite number of marbles in it. This is also a bag that has marbles in it, but the number of marbles in it is infinity. Right? Yeah. Now, when it comes to digital signals, a circuit designer has absolutely no problem considering that as a digital signal, even though the domain is the set of reals. Okay? So we don't want to go into those kinds of discussions and the merits of using that definition or this definition. What's important is to stick with continuous time, discrete time. That has no controversy around it. It's very simple. A continuous time signal is a signal whose domain is uncountable. A discrete time signal is a signal whose domain is countable. That's it. We remain silent about the range. Now, when you take more advanced courses like DSP 123, issues are discussed where you learn how to convert an analog signal to a digital signal, or to that kind of a digital signal. So notice think about what you're going to have to do with a signal like that to turn it into something like this, or to turn it into something like that. Let's start with this one. This one has a domain that's chosen from the rails. Okay, it's t, continuous time. So is the analog signal. So there's no discretization that has to take place along the time axis. What you have to do to convert that into a signal like this is to discretize the amplitudes. Amplitude discretization has a technical name. It's called quantization. And that's a topic for 2 courses beyond this one. You don't even learn it in 120. Okay? So we don't talk about that at all. To convert a signal like that to a signal like this, you have to discretize what? You don't have any restrictions in terms of the amplitude. So there's no need to discretize along the amplitude. What do you discretize? Time. That is a topic that we study in this class and in 120. And that process is called sampling. You sample this analog signal along the time axis. Think of it as a strobe light hitting the signal and capturing the value at various equidistant points in time. So that process of discretizing time is how we convert a continuous time signal to a discrete time signal. That is a legitimate topic that we talk about later in the semester. All right. There are some signals that you will become intimately familiar with and you will learn to love and hate as we go through this semester. So, important signals. In continuous time, I use CT for continuous time and DT for discrete time. These signals are the complex exponential, and its discrete time counterpart will be e to the I omega n. So t is the time variable, n is the sample. It's this one. I'll say a lot more about this later today. So this is complex exponential. But with an imaginary exponent. And same for this. Yeah? We broadly classify exponentials of this form, where S is a complex number, as complex exponentials. This more general class of exponentials, which are also called, complex exponentials really deserve to be allocated to this function. This brings in some subtleties that you learn in 120. We primarily focus on exponentials that are purely imaginary in this class, both in continuous time and discrete time. Okay? But in 120, so for EE 120, I'll describe what kind of a beast this is in this lecture, actually. It turns out that this function is important in 2 respects. First of all, we study a broad class of systems in this class whose responses to these complex exponentials reveal a lot about their behavior. So you take there's a broad class of systems in this class that we'll talk about later, called linear and time invariant, or LTI systems, that are completely characterized by the response to the complex exponential. So that's one way this signal is important. The other way is that you can decompose a large class of functions or signals into a combination of these complex exponentials. In other words, you can break down a very broad class of signals into a linear combination of different complex exponentials. So you divide and then you conquer. Okay? That's part of why those are two main reasons why this is important. And this is going to become your buddy for the rest of the semester, and its discrete time counterpart as well. Another signal that's very important is the impulse. Continuous time impulse, or the Dirac delta. This is a beast that we'll have to talk about in great depth because, strictly speaking, it's not even a function. I will just tell you what it looks, how we denote it graphically. With an upward arrow at the location where the argument is 0. The actual value of this arrow, the height of this arrow, is infinite. But what we care about is the area under that curve. Very subtle. We'll get to it in due time. Its discrete time counterpart is very easy. Discrete time impulse or the Kronecker delta. Kronecker delta is very simply defined as the lollipop of height 1 at the origin, and we denote that by delta of n. There's no subtlety about this discrete time function. Yeah, this Dirac delta, don't worry about the Dirac delta for now. Don't even think about it. It's just the counterpart for this. I have to spend almost an entire lecture talking about the properties of that delta. But this one is very easy. Lollipop, height 1. Height is not infinite. Height is 1. And it's only it's 0 everywhere else. So delta n is 1 at n equals 0, and it's 0 elsewhere. Very easy to imagine. It turns out that this delta function, be it in continuous time or discrete time, also is very important in characterizing the same class of systems that I talked about or alluded to earlier, linear time invariant or LTI systems. They get characterized not only by their responses to the complex exponential, but they also can be characterized in the time domain by their responses to the impulse. In other words, I mean, that's actually quite amazing that you give the system, a discrete time system, this lollipop as an input, and measure what the response is, and from that response, you know exactly what the characteristics are of the system. You've completely characterized the system. That's quite remarkable. So that innocuous-looking signal is very important. Think of it in another way. I told you that we can break down signals into combinations of these complex exponentials, both in continuous time and discrete time. That's much easier to imagine with this signal. Let's say I have a discrete time signal, 3 minus 1, 2.5. So let's say this is minus 1, 0, 1. And it's got other values elsewhere. So let's say this is my discrete time signal, some arbitrary discrete time signal. I can write this as a linear combination of scaled and shifted versions of the impulse. How can I do that? Can you break this down? Let's say it's 0 everywhere else to make things simple. So talk to your neighbors and tell me graphically how you're going to break down this signal into a linear combination of scaled versions of these and shifted versions of these. Exchange names, phone numbers, emails, mother's maiden name, social security number, whatever. Okay. So now for these examples about which I ask questions in class, I usually want one loudmouth to be the starting point of the questioning. And the way it works is this. So once this person volunteers or we identify that person, every time I ask my first question in lecture, I will call on that person, and he or she will either choose to answer the question or pick somebody else. Okay? Usually they choose to pick somebody else. And then the person who gets picked will take a stab at the question. And then when we get to the next example in the class, that victim will pick the next victim. And this is how we keep you on your toes. So you can't sit here passively when I ask questions, because then you're going to, get embarrassed when we pick you and you don't know how to answer the question, and just that doesn't look too good. No pressure! So who wants to be the... Okay. What's your name?
I go by Meatball.
Meatball! Oh, I love you already, man. All right, Meatball. Now, what's your real name?
What?
What's your real name?
Amit.
Amit. Okay. You don't look Indian.
Oh, no, it's Middle Eastern.
Ah. Okay. So, Amit, do you want to give it a shot yourself, or do you want to pick somebody?
I'll give it a shot.
Okay. Go for it.
Okay, so should I just read it out to you?
Tell me how to draw it.
How to draw it?
Yep. How to draw the decomposition. So how many non-zero values do you have?
3.
So I want you to tell me what the 3 functions are that I have to add to get back this.
So just each of the 3 lollipops.
Each of the 3 lollipops, which is the one at -1, the one at 0, and the one at 1. And that's height 2.5. Figure not drawn to scale. Now, if you were to use the symbol delta to specify what this function is, what would you say?
I would say
That-
this is 3, so I take 3 in the bottom. Multiply that by delta, and since it's shifted from the origin, I do n plus 1.
N plus 1. Very good. Okay? And this one?
Very similar, -1 times just delta n.
Delta n. And this one is 2.5 delta n minus 1. And that's exactly how we've decomposed x as a linear combination. So linear combination, you've got 3 minus 1, 2.5 times each of the corresponding deltas added together. That's where you get the linear combination of shifted deltas. So x of n, we say, is equal to 3 times delta n plus 1 minus delta n plus 2.5 delta n minus 1. And that's your decomposition for this particular signal. Now, it doesn't take a whole lot of imagination to figure out that you can do this for any arbitrary signal, x. Right? If I want to write an expression for an arbitrary, so let's write the expression for this in more generic terms. So I've written x of n as what is 3? What is the number 3? Yeah, but it's x at. No, my question is much simpler than this. It's x evaluated at -1. So it's x -1 times delta n plus 1 plus x at 0 times delta of n plus x at 1 times delta n minus 1. Okay? Now, if I want to, for an arbitrary signal, I can write x of n as, potentially it extends over the entire set of integers, so dot, 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 plus x minus 1 delta n plus 1 plus x 0 delta n plus x1 delta n minus 1 plus dot, 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 plus the mth term is xm delta of what? N minus m or plus m? Minus m? Plus m? Very good. I take great joy at throwing monkey wrenches your way. So I can write it in terms of an infinite sum. X m delta n minus m. These infinite sums throw off a lot of people in the first semester. They have less trouble second semester because they've already been humbled by 1 semester of Berkeley. Anytime you have trouble understanding what a summation, whether finite or infinite, tells you, please write out a few terms to see the pattern. I've gone in the opposite direction here. So you can imagine what I'm doing going from here to here. But very often you don't see these steps. All you see is the summation, and you got to make sense of it. If it's not clear to you what that summation is doing, write out the terms. So you go from here to here, and then you see the pattern. Okay? Plug in some adjacent values of m, or whatever the index of the summation is, and write it out, and it'll be clear to you what it is. So any arbitrary signal can be decomposed into a linear combination. These are the coefficients now. The xm's become the coefficients. The values of the signal at different lollipops become the coefficients of shifted impulses. Okay? So I've broken down an arbitrary signal into a linear combination of shifted impulses. Now, if a system is such that it is completely characterized by its response to each of these impulses, then you know exactly what the response of the system is to an arbitrary input. And we'll say a lot about that later. Okay. Now, let's go to the complex exponential. What about the complex exponential? Actually, let me show you a demo, just by way of a bonsai break. Let's do a demo. This is from the yet-to-be-updated Ptolemy website for the class. I'm going to lose my computer from all this chalk dust. Let's do that. It's supposed to be on. Oh boy. Let's see if I can move this. Okay. So I will show you soon that the complex exponential is a phasor, the yellow one that you see, that rotates around the circle of radius 1 that we call a unit circle. I'll develop that story for you. So this is e to the I. E to the IT would be the phasor that, actually, let me make that e to the IT. 1 hertz. It's the phasor that goes around the circle once every second. Okay, that's e to the IT. What it was before, since we don't want to go dizzy, is that I've changed the frequency to 1/4 of a hertz. So you can follow what it's doing. So this is e to the I 0.25 t. Or e to the I 0.25 times 2 pi t. So essentially, it's an arrow that goes around the unit circle, and we'll explain why that is. Now notice, I can combine a whole bunch of these phasors. So this arrow that's going around the unit circle is called a phasor. When the frequency is positive, it's going counterclockwise. When it's negative, it goes clockwise. You can combine a whole bunch of these phasors to create interesting signals. So for example, right now in the bottom you see the projection onto the horizontal axis, and that's essentially a cosine wave. But you can create other types of signals. Here's a sawtooth signal in the bottom. It's an approximation to a sawtooth signal. Notice how many of these phasors are being combined to give you that sawtooth. What this means is that the sawtooth signal can be decomposed into a combination of these phasors, or of these e to the I, whatever frequency, t. And that's part of the reason that I mentioned the complex exponential is so important, that we can decompose signals, fairly general signals, into a linear combination of these, what you see as blue phasors, or blue complex exponentials, each with a different amplitude in front of it, and each rotating at a different frequency. I can do that with a square wave. So this is an approximation to a square wave. To get it almost perfectly, to not have these glaring ripples, you need to increase the number of complex exponentials that you use. Here we're only using 1, 2, 3, 4, 5. And that's why this signal is a finite approximation to the square wave signal. If I'm allowed to increase the number of these phasors that I use, I can approximate the square wave signal much more closely. And here's the triangle. This is much cleaner. See all those blue vectors are different complex exponentials rotating differently, and we've superimposed them. So we put the tail of each on the head of the other, and we take the vector sum, that's our linear combination, that carves out the triangular wave that you see. Okay? All right, let's... So the ability of the complex exponential to create... What did I do with my chalk? The ability of different complex exponentials to get together and carve out different types of functions that are useful to us is one of the most important properties of the complex exponential. And that's the whole discussion that we'll have when we talk about Fourier series and Fourier transforms in the last 1/3 of the class. So we can decompose signals in terms of impulses or in terms of complex exponentials. And each of those will reveal different properties of the signals and systems that we deal with. The impulses tell us what's happening in the time domain. The complex exponentials reveal information about the frequency domain behavior. And remember I said we look at signals and systems from two angles, different but very much related. Frequency domain, time domain. Sometimes it's easier to see things in the time domain. Sometimes it's easier to see things in the frequency domain. And our ability to hop between these two domains is very important. And we'll be doing that, doing a lot of that in this course. So what is this magical e to the complex exponential? What is e to the, let's not even talk about omega yet. Let's talk about this complex exponential. I'll give you the short answer, and then we'll, for whatever time we have in this class and the beginning of the next class, we'll justify it. It's essentially a phasor that rotates counterclockwise on the unit circle these buzzwords you should get familiar with. So this is the circle of radius 1. At the rate of one revolution per second. Oh, sorry. No, that's not one revolution. One revolution every 2 pi per 2 pi seconds. No, one revolution. Oh, yeah. Sorry. I should have put pi. This annoying 2 pi will come into the picture all over the place. E to the I 2 pi t takes you one revolution in 1 second. So when you start off at time 0, what's the value? E to the 0. 1. When you go to time 1 second, you have e to the I 2 pi. Most of us still don't know what that is. And I hope you did some of that in the discussion section yesterday. But you need to read Appendix B, and I'll do some of it here to understand. But essentially, you live in the complex plane, real axis, imaginary axis. You have a circle of radius 1. If this is 1, what is this? Minus 1, what's that? I, which is the square root of minus 1. And this is minus I. Okay? So the particle, if you can think of this as the position of a particle in the complex plane, you start off at time equal to 0 here. And after 1 second, you go around the unit circle, 2 pi radians. So you're back where you started. And let's see why that happens. What is the expansion of e to the z that you're aware of? The Taylor expansion. One plus z squared over 2 factorial plus z to the n over n factorial. So e to the z has an infinite sum, which is z, whoops, too many variables. You liked n, so we keep it n. Z to the n over n factorial. Okay? What happens when z is equal to I omega t? So I'm looking at e to the I omega t, which is the complex exponential I'm after. So I have 1 plus I omega t. Where do you get the minus from? I squared. Omega t squared over 2 factorial plus, or is it plus? Minus I omega t cubed over 3 factorial Now, because we're running out of time, I'm going to help you with a couple of expansions that you have no reason to memorize. Cosine omega t, which is 1 minus omega t squared over 2 plus omega t to the 4th over 4 factorial minus so on. And sine, which is omega t minus omega t cubed, basically all the odd powers, plus omega t to the fifth minus so on. Now, can you write that top one in terms of cosine and sine? How? E to the I omega t is equal to cosine omega t plus I sine omega t. This is a very important formula. In fact, you can write it more simply. E to the I theta is cosine theta plus I sine theta. This is called Euler's formula. It's developed in Appendix B. And this is what makes it clear why e to the I omega t, or e to the I theta, is actually sitting on the unit circle. Because look at the magnitude of this complex number. This is a complex number, right? This is the real part. This is the imaginary part. What's the magnitude of this number? Y. So here we have alpha plus I beta. This is a complex number. What's the magnitude? It's what? Square alpha plus square root. Right? So what happens when you do that to this number? E to the I theta is equal to square root of what? Cosine squared plus sine squared. And that's what? 1. So this is one of the golden rules in this class. The magnitude of the complex exponential that has a purely imaginary exponent. So theta is real. Omega t is real. The magnitude of such a complex exponential is 1, which means your e to the I omega t, or e to the I theta, is always sitting on the unit circle. So e to the I omega t always sits on the unit circle. It's perhaps easier to talk about e to the I theta. So let's draw that. Real axis, imaginary axis, unit circle. Okay? E to the I theta, where is it located? Its real value is cosine theta. So let's say e to the I theta is sitting somewhere on the unit circle. Its real value is cosine theta. How do I draw that? What do I have to do from this point? Draw a line to where? Project onto the real axis. And this has got to be cosine theta. And its imaginary value is I sine theta. So I got to do a perpendicular here, and this has got to be I sine theta. What point on the unit circle has the property that when I project it onto the horizontal axis, I get a cosine theta, and when I project it onto the imaginary axis, I get the sine? What is this? So if I were to draw an arrow to that point, what are the features of that complex number? What is the angle that it's making with the horizontal axis? A what? Theta. This is theta. It's the arrow that's making an angle theta with the positive reals. It's sitting on the unit circle. This is a circle of radius 1. So when I project it, I get cosine. When I project it this way, I get sine. That's from high school trig. Okay? So e to the I theta is the point on the unit circle that makes an angle theta with the positive real axis. Now what about e to the I omega t? Why do I keep carrying this annoying omega t with me? What's so special about e to the I omega t? What feature am I trying to bring out? Movement. Movement. E to the I omega t, you can think of as the position of a particle in the complex plane. And this particle moves as time goes forward or backward. So as time moves, as t varies, this particle moves. Where is it restricted to live? On the unit circle. When time is 0, where is it? At 1. So this is e to the I omega 0, which is e to the 0, which is 1. And as time goes forward, assume omega is greater than 0. Let's say omega is 2 pi. Omega is 2 pi. And time now starts going forward. Okay? Which way does the particle move? This way. At t equals 1, where is it going to be? It's going to be at e to the I 2 pi, which is back where it was. At 1/4 second, where is the particle going to be? 1/4. E to the I 2 pi at 1/4 second. At I. E to the I 2 pi times 1/4 second, which is e to the I pi over 2. So what do you know about e to the I pi over 2 and its relationship to I? They're equal. See, these are all the manipulations that you're going to get quick at, or you should get quick at, very soon. I'm out of time, so let me just write this. E to the I pi over 2 is equal to I. Can you tell me what the number minus 1 is? E to the I pi, or e to the minus I pi. I can go pi this way or pi that way. Doesn't make any difference. I get to the same point. Whether I go pi forward or pi backward, it doesn't matter. So what is minus I? E to the I. What's the angle? 3 pi over 2. And the number 1 is e to the I 0, which is e to the I 2 pi, which is e to the I 4 pi, which is e to the I 2 pi k. Okay? All right. See you next week.